Hello everyone, my name is Zhengxiang Qiu. I am a second-year postgraduate student at the University of Science and Technology of China. I am very pleased that our work, Accelerating Diffusion Transformer via Gradient Optimized Cache, has been accepted by ICCV. Next, I will introduce this work. This presentation consists of the following 4 parts. First, I will introduce the background work related to caching and the motivation behind our work. Previous sampling acceleration methods are mainly divided into 2 categories. One is to use pruning and quantization to reduce the time required for each sampling step, and the other is to optimize the information transmission method in the sampling process to reduce the number of sampling steps. In the past 2 years, many methods for accelerating sampling through caching have emerged. These methods reuse previously computed information to skip subsequent calculations, thereby achieving better generation results. Next, I will briefly introduce the development path of caching. Deep cache is the pioneer of diffusion caching. It reuses intermediate parameters and inputs them at the same position in the next step, thereby skipping most of the calculations of the UNet in the next step. Fora was the first to extend the caching strategy from UNet diffusion to diffusion transformers. However, the aforementioned methods all focus on finding positions that are unimportant for sampling and caching them. They do not consider how to address the inevitable errors caused by caching. Therefore, when the caching intensity increases, the generation quality drops sharply. To solve this problem, we propose GOC gradient optimized cache to reduce caching errors. Next, I will talk about the implementation of GOC and its experimental results. As shown in the left figure, traditional methods directly replace the blue part with the green part, which leads to certain errors. As shown in the right figure, the original error is represented by the red arrow. By using gradients, we can convert this error into a shorter green arrow, thereby reducing caching errors. The figure below shows the pipeline of GOC. The brown arrows represent the traditional naive cache, and the purple arrows represent GOC. First, we define the different modules of the original diffusion transformer model. Naive cache reuses the calculation outputs of attention and MLP at time step t to accelerate generation. After the gradient is formed in the first step, we record the cached features of the 2 most recent steps. When assigning values to the cache next time, we calculate the difference between the cached contents of these 2 previous steps and embed this difference into the original cached features, thereby offsetting a portion of the caching errors. However, during the model sampling process, there may be an inverse gradient phenomenon, which leads to gradient errors. Through calculation, we avoid applying GOC to steps where the probability of inverse gradient is high or to the later steps. Next is the experimental part. The upper figure verifies that gradient caching achieves good performance in most steps. In the 17th step shown in the lower figure, the details such as the head of the beetle are distorted. This is because the gradient error is too large and the model cannot map it back to the normal range in time. The table shows that GOC achieves the best generation quality. As can be seen from the figure below, our method can improve generation quality while eliminating artifacts. This table presents our experimental results on the value of eta under different caching strategies. These 2 tables prove that GOC achieves excellent results when applied to rule-based caching represented by Fora and training-based caching represented by learning to cache. Meanwhile, it hardly increases the sampling time. This page demonstrates the effectiveness of GOC in the text-to-image task. Finally, let's move to the conclusion. The advantages of GOC include, no training is required, it can be easily deployed on existing DIT models or based on existing caching methods, and it can significantly improve the generation quality after caching. However, it also has shortcomings. GOC only considers linear fitting errors, which is not sufficiently consistent with the actual sampling process. Thank you for watching.